Alright, hello class. In this video we're going to be talking about Lagrange multipliers, and not just that, really we're going to be talking about finding absolute extrema over constraint curves. Okay, and there are essentially two ways to do it. One is with Lagrange multipliers, and the other, there are different ways we can go about doing it, but it often boils down to making a vector valued function or some kind of simplification of your constraint curve to basically restrict your surface down to a single curve. Okay, so let's just look at an example. I think an example is the easiest way to decipher what exactly is going on. Alright, so let's find the absolute maxes and mins of this surface here. Let's call it z, or f of xy equals x squared plus y squared minus 2x plus 2y plus 5. Okay, subject to the constraint curve, x squared plus y squared equals 4. Now, often the constraint curves are given generally as this form, g of xy equals 0. Alright, so in this case, our g of xy would be x squared plus y squared minus 4. Okay, so we could call that a particular constraint curve, alright, for our surface. All right, so what does this actually mean? Well, let's take a look at a graph. Okay, so here is the surface that we're looking at in red. So that's our f of xy equals x squared plus y squared minus 2x plus 2y plus 5. That is a paraboloid that's been shifted over. Okay, that's all it is. Now here's the constraint curve, or constraint surface. This is g, that's just z equals g of x comma y. However, when we set it equal to 0, okay, what we get is simply what's going on the xy plane, which is this circle. So we can forget about this for a second, okay, and we have this circle. So this is our constraint curve. X squared plus y squared is equal to 4, so that's just a circle centered at the origin with radius 2. Okay? Now, what we mean by saying that we want to find the absolute max and min of this surface constrained to this curve is basically this. We're going to map this blue circle up, okay, and see where it intersects the surface here. That's this curve. Okay, so this is what we're talking about. We want to find the absolute max and min of the surface on this red line I just put on top of the surface itself. So all we're really doing is looking directly above this circle, and we're charting out this path along the surface, which gives us just like a curve around this bowl, right? And what we want to do is find the absolute max and min along this red curve. Okay, so just looking at it, it looks like we have a maximum here, right? And a minimum, well, it's kind of hidden now, but when it comes back around, it looks like we have, let me just do this, a minimum there. Okay? Now, if we were looking for what was going on inside the circle as well, it'd be a different story. But all we're looking at is the boundary, right? What's happening on or over this circle. Okay, so if I flip this around, okay, that should be a little easier to see. So when we flip this up, we see that this red curve completely covers the blue curve. All right, so from above, they look exactly the same. And so we want to find these 2 points. Okay, so let's take a look at how we go about doing this. All right, so to do this without introducing any sort of new concepts, all right, what we would do is this circle, right, can be parameterized as a vector value function. So this curve as a vector valued function would be, we could say it's r of t equals the vector valued function 2 cosine t and 2 sine t, and that's for t going between 0 and 2 pi. Okay, so that is one way to parameterize this. This is one way to get this simplified. So what we're essentially doing is saying that x is 2 cosine t and y is 2 sine t. Okay, so what we can actually do is rewrite our surface f of xy in terms of just t, right? Because we can write x as a function of t and y as a function of t. So we could actually say that z completely in terms of t is f of x of t comma y of t. Okay, and now we will just replace all of our x's with the 2 cosine t and all of our y's with the 2 sine t. Okay, so z of t will be, well, x squared, that will be 4 cosine squared t, plus y squared will be plus 4 sine squared t, minus 2x, so that will be 2 times 2 cosine t, so that will be 4 cosine t, then plus 2 times y, so 4 sine t, plus 5. The 5 doesn't change. And cosine squared plus sine squared, that's 1, so this whole thing here comes out to be 4. Right, so the whole z of t, okay, is 9 minus 4 cosine t plus 4 sine t. Okay, so what this gives us is now the vector valued function that models this curve here, okay, is this. Let's call it c of t for the curve. It's going to be 2 cosine t, 2 sine t, and this z of t we just found. So I'll just, instead of rewriting this, I'll just say comma z of t. Okay? And if we want to find these 2 points, right, this maximum and this minimum, okay, what we need to do is basically what we're trying to do is maximize and minimize the height, because we're talking about maximizing and minimizing the z value. Okay, so we don't have to worry about what's going on here. We just want to optimize. So maximize / minimize z of t. Okay, that will give us the maximum height and the minimum height. Okay. All right, so to do that, this is now a Calculus 1 problem. Right? Because to optimize just a single variabled function like this, well, we just take z prime of t. So the 9 disappears. We'll get 4 sine t plus 4 cosine t when we take the derivative. We're going to set this equal to 0. right? So here we're going to find the critical points. Okay, and well, now we're going to solve this. So how I would solve this is like this. I would move the sine over to get 4 cosine t is equal to negative 4 sine t. Then I'll divide by the cosine, or 4 cosine of t on both sides to get 1 is equal to negative 4 sine t over cosine t. Oops, 4 cosine t. Of course, the 4's cancel. And sine over cosine is tangent. So what we basically have is that 1 is equal to negative tangent t. And what we really want is this. We want, when does tangent of t equal negative 1? Well, tangent of t is going to equal negative 1. Well, tangent equals 1 at multiples of pi over 4. But we need it only in quadrants where sine and cosine have opposite angles, right? So this is going to be t equals 3 pi over 4 and 7 pi over 4, right? Quadrant 2 and quadrant 4. Okay, sometimes I have to draw the picture here, so that was terrible. Let's try that again. Yeah, so 45-degree angles, and here this is where x is negative and y is positive, and this is where x is positive and y is negative. So tangent is going to be negative 1 in these two quadrants at these two angles. Okay, so this is, or these are the critical points. Okay, and since we're only looking for absolute max and mins, we just need to plug this back into our z. Okay, so let's plug back into z of t. Okay, so z of 3 pi over 4 will be 9 minus 4 cosine of 3 pi over 4 plus 4 sine of 3 pi over 4. So in quadrant 2 here, right, if our x is negative, that makes our cosine negative, and our y is positive. Okay, so it's going to be 9 plus 4 times root 2 over 2 plus 4 times root 2 over 2. Okay, so we're going to get, and the 2 is going to cancel with the 4. Let me use a different color here. Okay, so we're going to get 9 plus 4 square root 2. All right, then when we plug in 7 pi over 4, whoops. All right, we go ahead and plug that in. Okay, they're both going to be root 2 over 2 again, except now we're in quadrant 4, so here the cosine will stay positive, but the sine will be negative. So in this case, we're going to get 9 minus 2 root 2 minus 2 root 2. So here it's 9 minus 4 root 2. Okay, so this here, this should be the maximum, and this should be the minimum. All right, so now that we're back at the graph, let me drop the surface real quick. All right, I just want to see the constraint curve we're working on. And when I put the points back in, well, you'll see we have negative 1.41, comma 1.41. Oh, well, that I didn't mention. If we go back here and put in these t's that we found into our x and y coordinates, that's what we're going to end up getting. We're going to get 2 root 2 essentially, okay? Or really just root 2. Let's just go ahead and do it. Okay, so showing is often, almost always, better than just telling. So at this t value here, we'll get the point negative root 2, this thing. And here we'll get the point root 2, negative root 2, this thing. So when we go back to the graph, we can see that the maximum occurs at the negative root 2, and that comes out to be about 14.66. And then here we get the root 2, negative root 2, comma 3.34, which is what the other one comes out to be. Okay, so that does line up with what we see here graphically. All right, so if all of this seems rather complicated, it is. All right, I'm not going to argue with that. However, there's another method that we can use that doesn't really require us to parameterize that curve C and go through that parameterization and the vector valued function and all that. It's called the method, or the Lagrange Multiplier method. Okay. Okay, and the Lagrange Multiplier method, it's for solving the same type of problem. It's for optimizing z equals f of xy over the constraint curve g of xy equals 0. So from our previous example, we had we of course had these functions. Now, if we go back to the graph, okay, here's what the Lagrange multiplier idea is based off. It's based off the fact that gradients are perpendicular to level curves. Okay, so for example, I want to look at the gradient of f at the negative root 2, and the gradient of g at negative root 2. That's where our maximum was. Okay, so if we look at the graph, here is the gradient of f at that point, and I put it up on the surface itself. Okay, so if we look at it from above, we see, like we have always, that the gradient is always it's going to be perpendicular to if we made a level curve. So actually, let me put the level curve of this surface here. All right, so here we go. We have that, here's the level curve at this height. And of course, the gradient is perpendicular when we look at it above. It's perpendicular to this level curve. But notice it's also perpendicular to the constraint curve. Right? If we actually drop the constraint curve and just look at the blue curve, right, there's the constraint curve. The gradient of f is perpendicular to all three of these curves, right? The gradient of f. Okay? Now, if I put in the gradient of g at 0, so this is actually, if you remember, the level curve of this, where was it? Of this function. This was z equals g of xy. We dropped that because it's not that useful, but this is the level curve of that function when z is equal to 0. And if we take the gradient of g, right, here's the gradient of g, we see that at the same xy point, these two gradients point in the same direction. They're parallel. Okay? So it turns out that the gradient of g is just going to be a multiple of the gradient of f, or vice versa. All right, so at a critical point over the constraint curve, all right, the gradient of f will be parallel to the gradient of g, and so gradient f and gradient g will be multiples of one another. In other words, the gradient of f will equal some constant that we'll call lambda times the gradient of g. Okay, this is the Lagrange multiplier. All right, so lambda, that's the Greek letter lambda, okay, is called a Lagrange multiplier. Okay, and it can help us find the absolute extrema over C. Okay, so I think, once again, it's probably easier to just see how this works in practice with an example. So let's do that. With this example we have here, let's use the Lagrange multiplier method to help us find the absolute extrema over C. Okay, so I'm going to move to a new page and we'll do that. Okay, so here we go. And remember, our Lagrange multiplier method tells us that the gradient of f is equal to some constant times the gradient of g. Okay, so basically what we want to do is find x, y, and lambda that satisfy this, and g of xy equals 0. Okay, so let's take a look at how this would go. So first of all, of course, we need to find the gradients. So the gradient of f, well, that's going to be, in the first component, it will be the x derivative, so that will be 2x minus 2. Okay, and then in the y component, we're going to put the y partial derivative, so that will be 2y plus 2. All right, now for g of xy, to find its gradient g, well, once again, it will be 2x comma 2y. All right, so now we're going to set up the fact that gradient f needs to equal a constant times gradient g. Okay, so this is going to essentially give us two equations, because what we have is 2x minus 2 comma 2y plus 2 is equal to some constant lambda times 2x comma 2y. All right, well, this is a constant or a scalar, so what we have is 2x minus 2 comma 2y plus 2 is equal to, let's distribute this across, 2 lambda x comma 2 lambda y. Or you could do 2x lambda, what have you, either way. Okay? So this gives us essentially two equations. We have that 2x minus 2 is equal to 2 lambda x, and that 2y plus 2 is equal to 2 lambda y. All right, now what I'm going to do is divide everything by 2. No reason to have all those 2's laying around. So this gives us that x minus 1 is equal to lambda x. and y plus 1 is equal to lambda y. Okay, so where do we go from here? And what I'm going to stress here is either method that you decide to use, I call it the law of conservation of misery, right? It's going to be pretty gross either way. However, in a lot of cases, this Lagrange multiplier idea ends up being a little nicer. Alright, now from here, there are lots of ways we could solve this. I am going to solve, let's call this equation 1 and this equation 2. Okay, so there are a lot of ways to solve this particular problem. One thing we can do, I'm just going to start here because I could just move that y over and get 1 is equal to lambda y minus y, or y times lambda minus 1. Okay, well that maybe seems like an odd, an odd thing to do, but if I were to divide this through to get y is equal to 1 over lambda minus 1, okay, that's something, I guess. Now, let's solve equation 1. So equation 1, if we do it in the same, essentially the same way, we'll get negative 1 is equal to lambda x minus x, so that will be lambda times, other way around, that will be x times lambda minus 1. Oh, okay. Well, if we divide this through then, we get that x is equal to negative 1 over lambda minus 1. So that means that x is equal to negative y. Okay, so that is the important part. Now you might be thinking, well, hang on, how does this actually help us? Well, it helps us because now if we go back to g, right, g of xy equals 0, this gives us x squared plus y squared is equal to 4, and with x equals to negative y, we put that in as negative y squared plus y squared equals 4. Okay, well, negative y squared is just y squared, so this comes out to be 2y squared is equal to 4, so y squared is equal to 2, giving us that y is equal to plus or minus the square root of 2. Okay, so I'm going to call this statement here star, and this statement here, let's call it heart. Okay. Now, from star and heart, well, y is plus or minus root 2, and then star tells us that x is always negative y. So, from star and heart, we get the points okay. Well, when y is square root 2, x is going to be negative of that. And when y is negative root 2, we get the negative of that, which is positive root 2. And that here, those are the same exact values that we got doing it the other way. Okay, so it turns out that we can actually use this method, as funky as it seems, right? The solving can be a little weird. However, what you're aiming for is to get something that you can maybe reduce back down into the g of xy equals 0 and be able to solve some things. So we aren't necessarily trying to solve for lambda, right? Lambda is just sort of like this bridging gap to help us get where we're going. What we really want are points in terms of x and y. All right, before we move on to the next example, I want to show that here we were making a pretty big assumption that lambda was not equal to 1, right? Because if so, we would be dividing by 0. However, if lambda were equal to 1, what would happen here in equation 1 is we would get x minus 1 equals x. And the x's would cancel, and we get negative 1 equals 0, which is total garbage. So this is a safe assumption to make because lambda is not going to be 1, or else this would all fall apart. Okay, I just wanted to specify that before we move on to the next example. All right, so let's look at another example here. If we want to find the absolute extrema of f of x y equals e to the xy, subject to the constraint x squared plus y squared over 4 equals 1. So this constraint here, this is an ellipse. Right? So what we need to know about this is with this ellipse we go out 1 in the x direction and 2 in the y. Okay? Horrible graph, of course, as usual. Maybe I can make it a little better. There we go. Okay. So this curve here, right, gives us a graph that looks something like this. So here's our surface, e to the xy, strange looking little guy here. And here's the ellipse that we're looking over. And when we map that up, we get this strange little curve here. So we want to find essentially these points, whichever one might be higher. And it looks like our minimums will be somewhere around here. Okay. All right. So let's see which method actually ends up being easier for us, the parameterization method or the Lagrange multiplier method. Okay, so for the parameterization method, we need to parameterize this ellipse. So that ellipse would be something like r of t equals, it would be cosine t, comma 2 sine t. Okay, so that would be our x and our y. All right, so if we put that into our f to make our, let's say, our z of t function, right, it would be e to the cosine t times 2 sine t. And let me tell you something that will make this problem a lot easier to do is this identity here. So this trig identity, which is that sine of 2t is equal to 2 sine t times cosine t. Okay, so we can bring this together to be simply e to the sine of 2t. Okay, we don't have to do this, it's just going to make it 1,000 times easier because now when I take the derivative, z prime of t, we're going to get, well, derivative of e to the stuff is e to the stuff left alone. Then times the derivative of the stuff. So that's going to be cosine of 2t times 2. Okay, so it's really just going to be 2 cosine of 2t e to the sine of 2t. All right, now you might be thinking that this looks horrible because now we have to set this equal to 0 and solve, but I'll set your mind at ease a little bit with the fact that this e to the stuff is always positive, right? So we can just ignore it, and mainly what we're trying to do is see when, and the 2 is not going to bother us out here either. Really, all we need is to know when cosine of 2t is equal to 0. All right, well, let's ignore this for just a minute. All right, we'll come back to it, but I want to think about what angles causes cosine to be 0 in the fundamental cycle. And so I didn't mention it here, but we're basically looking at just a single rotation, a single full rotation along this ellipse. All right, so what angles make cosine equal to 0? Well, that's going to be pi over 2 and 3 pi over 2. Okay, well, we don't have just cosine, we have cosine of 2t. Okay, so I'm going to take this out a little further since I have a bit more. So the next one up would be 5 pi over 2 and 7 pi over 2. And the reason I want to do that is because my t is between 0 and 2 pi, but if I look at 2t, 2t is going to be between 0 and 4 pi. So I need to go all the way out to 4 pi to get all the possible angles that would work here. Okay. If you're confused on this, I do have videos on my channel talking about how you solve trig equations in more details. It's probably been a while for some of you. But the reason we need to do this is because when I divide by 2 now, I'll get t is equal to pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. And those are all of the possible values of angles between 0 and 2 pi that will cause cosine of 2t to equal 0. Okay, so here are the critical points. And now we just need to plug them in and see which is the highest and the lowest. Okay, so for z of pi over 4, that's going to be e to the sine of 2 times that, so that will be sine of pi over 2, so that will be e to the 1. Sine of 3 pi over 4, that will be e to the sine of 3 pi over 2, so that will be e to the negative 1, or 1 over e. 5 pi over 4, it's going to give us e to the sine of 5 pi over 2, which will be simply e, and then z of 7 pi over 4 is going to be e to the sine of 7 pi over 2, which will be e to the negative 1 again, or 1 over e. So our absolute maxes happen here at these 2 points, and our absolute mins happen here. Okay, when we look at the x and y values at these points, okay, they're all going to be essentially multiples of root 2 over 2 and root 2. So, okay, and putting this all together, I have the points for my maximums are root 2 over 2, comma root 2, e, and negative root 2 over 2, comma negative root 2, comma e. Those are the maxes, and the mins are going to happen. So these are in quadrant 1 and 3, and these are going to be in quadrant 2 and 4. So our x will be negative, our y will be positive, whereas here our x will be positive and our y will be negative. So notice it's the same, pretty much same values, and that's just because we're at multiples of 45 degrees here. Okay, and let me go back to my graph and plot these points and see if they jive with what we just found. Okay, so here we are back to the graph, and I've put these points in that we just found. And as you can see, at the multiples of 45 degrees, okay, let me look at it from here. The multiples of which we have to be careful about that when we're thinking about an ellipse. But at these points along the ellipse here, we see it actually jives with what we found. Okay, our max, here's a max here, here's root 2 over 2, root 2, and e. Here's an absolute min here. It's kind of hard to see there. Maybe that's a little easier there. Actually, let me get rid of this. There we go. That's much better. Here we go. That's negative root 2 over 2, root 2, and 1 over e. Okay? All right, now let's take a look at solving the same problem, but with the Lagrange multiplier method. Okay, so for the Lagrange multiplier method, what we need to do is set the gradient of f equal to lambda times the gradient of g. Well, g is not this exactly. G of x, y is going to be, it's essentially x squared plus y squared over 4 minus 1. Okay, so the gradient of f, well, the gradient of f, it will be e to the stuff times the derivative of the inside. So it will be y, e to the xy, okay, comma, and then it will be x, e to the xy. All right, then it will be lambda times now the gradient of g. So that's going to be 2x, comma, 1/2 y. All right, now there are lots of ways to approach this from here, because what we end up with is that y e to the xy is equal to 2 lambda x, and that x e to the xy is equal to 1/2 lambda y. Okay, now this is, like I said, a lot of ways we can approach this, but I have a tricky little thing to try to show you. I don't really want to divide by these variables because I don't want to say that, you know, they can't be 0 or what have you. If I were to multiply this guy here, this first equation, by x, and this second one by y, what we end up with are these two new equations. So multiplying both sides by x, we'll have xy e to the xy is equal to 2 lambda x squared. And in the second equation, we'll have xy e to the xy is equal to 1/2 lambda y squared. Now, why did I do this? What made me think of this? It's the fact that the left-hand side of both of these equations are almost the same. They're only missing, well, what the other one's missing, right? This one's missing x, this one has it. This one's missing a y, but this one has it. So if I multiply these two, what that tells me is now these two guys are exactly the same. So I can actually get rid of that completely and say that these two are equal to one another. So this leads us down to this, that 2 lambda x squared is equal to 1/2 lambda y squared. Okay, so let me move this 2 over to get that 4 lambda x squared is equal to lambda y squared, and we can cancel out that lambda because, you know, it's not going to change anything. The only thing, again, we have to worry about is it can't be 0, but that's already true from here, so we don't have to worry about that here. And so we get 4x squared is equal to y squared. Now we can take the square root of both sides and get plus or minus 2x is equal to y. Okay? So like before, now we're going to plug this into the g of xy equals 0. Okay, or just the constraint curve itself. All right, so you just apply this to C. Well, if y is equal to negative or plus or minus 2x, and our constraint curve was x squared plus y squared over 4 is equal to 1, plugging this in, we'll get x squared plus, so let me show you what I'm doing here. I'm taking this and putting it into here. So it will be plus or minus 2x all squared equals 1. So we'll get x squared, oh, and that's, sorry, over 4. Okay, plus, well now, the plus or minus goes away because we're squaring it. So it's going to be 4x squared over 4 equals 1, which gets us down to just 2x squared equals 1. So x squared is equal to 1 over, oops, jumped the gun there, 1/2. So x is equal to plus or minus the square root of 1/2. Okay, so that can actually simplify right to plus or minus root 2 over 2 when you rationalize the denominator. And that is actually what we ended up getting. Okay, before, if you remember, our x's were root 2 over 2 or negative root 2 over 2, and now we have y is plus or minus 2x. So when x is positive root 2 over 2, y is plus or minus 2 times it, so root 2. Okay, so this gives us root 2 over 2, root 2, comma root 2, and negative root 2 over 2, whoops, sorry, no, I'm still root 2 over 2, comma negative root 2 over 2. And then when x is negative root 2 over 2, then we get y is, once again, plus or minus square root 2. So we get negative root 2 over 2, comma root 2 over 2, and then negative root 2 over 2, comma negative root 2 over 2. Okay, so you see here we got all the possibilities, and so to figure out which is the absolute max or min, then we go back and plug it into our z, which is here, our f. So we just plug these in to f to see which is the absolute max and which is the absolute min. Okay, so f of root 2 over 2, comma root 2, it's going to be e times root 2 over 2 times root 2. Well, check that out. The root 2's will become 2, so that's just e. Okay, when one of them is negative, like in this case, we still get the same idea, it just comes out to be -1 in the exponent, and so on. Okay, I spared showing you each little step here, same idea, but once again, we get the same absolute maximum, same absolute minimums doing it this way. Which way's easier? I don't think either, really. Honestly, it's more about comfort level, right? If you're more comfortable with getting things parameterized in an easy way, that's probably going to be your best bet. If you're better at just solving funky little equations like this. These always sort of remind me of like solving logic puzzles or something. Then the Lagrange multiplier method's probably the best way to go. In general, if you're programming, if you're writing a program to do this for you, the Lagrange multiplier method's probably a better bet. All right, before I close this one off, I do want to mention one thing. Don't get freaked out if you see that instead of a constraint curve, it gives you a less than or equal to. Okay, all that's telling you is if you have your constraint is x squared plus y squared less than or equal to 4, you take the circle of radius 2, okay, and then everything else on the inside. All right, so you do the boundary with the methods we just talked about. Okay, so this is actually called the boundary. That's our curve C is the boundary. The region enclosed, maybe we could call this A for the region. For A, you find the critical points of F just like you do in, just like we did in the last section, the max and min problems. And once you find them, then you just plug them into F along with the critical points you find on C. Okay, and so say maybe you find a critical point here and a critical point here, and maybe you find one out here, but you don't have to include that one, and then you find a few on the boundary. Okay, all you do is you plug all these in to F, all of them. All right, so you plug in all critical points to check. Okay, the inside ones and the outside ones, and that's it, right? So if we go back to this graph here, actually let's find just the critical points of just this F here. Shouldn't be too bad since the gradient of F we've already found just to do what we were doing before. Okay, and when we set it equal to 0, we'll basically get that x is equal to 1 and y is equal to -1. Okay, and that is just straight up. So we'll end up with the point 1, -1. Okay, so 1, -1 would actually be like here-ish. Okay, and so f of 1, -1 will be, when you plug that, okay, we'll get 3. So we'll have 1 minus 1 comma 3, and this should actually be the new absolute minimum when compared to what we found on the surface already. All right, so back to the graph. That was the first example we looked at. If I put that point in, you see what it's giving me is the bottom of that paraboloid. Okay, so if we're also looking on the inside of the circle, we just have to check those other critical points just like we did back in the previous section, but we don't have to go through the second derivative test because all we need to do is plug it in along with these values too, and it seems that this is pretty clearly the absolute minimum now, because before the absolute minimum we chose was 3.34, but now we have 3, so this will be our new absolute minimum. Okay, so don't think that it's something completely different if you see the less than or equal to. It just means you need to check inside of the region as well. Okay, so that should about do it for this section, and actually this completes the module. I will catch you all in the next video. Cheers!